Okay, this is going to begin our study of calculus. And in Chapter 11, which is where we begin, we're going to talk about something called a derivative. There are two parts of calculus that we'll use this semester. One is called the derivative, and it is based on the idea of limits, and we will discuss actually the meaning of a derivative. What it tells you is going to be a rate of change, which you think of as a slope, and that's not actually wrong, that is correct. But we're going to think of slope and a rate of change in a little bit different way in this class. The other part of calculus that we'll look at toward the second half of the semester is going to be something called integration. And integration is going to allow us to find the area between the x-axis and a curve that is defined by a function. It's pretty easy to find the area between the x-axis and a straight line because we could use geometry, but in calculus we're going to have to find it for curves like x squared and 2x plus 9 raised to the 5th power and things like that. So, you know, there's going to be some algebra involved, but it's not really algebra intensive. I'll tell you what you need to know as we go along. Our first section is going to be about something called limits, and limits actually applies to both the derivative and to integration later on. So it's an important idea, and I hope you'll be patient with me and with the course as we learn about limits, because I remember being where you are and thinking about how hard this whole idea was, that it seemed like it was so simple, and surely it couldn't be that simple because after all, this was calculus. Calculus is supposed to be hard. But the only advice I can give you here is advice that I was given too, and it was hard to take. But the best advice, honestly, is try to let it be as easy as it actually should be, because it is a little bit fuzzy as a concept, but the math itself isn't difficult. So, try not to worry about it. Eventually, the little light bulb will pop on that you'll say, oh, that's what that's all about. So let's begin. And in beginning, we're going to talk about things in the beginning, we're going to talk about things that you learned in previous courses. In previous courses, you learned how to deal with what we call static situations. Situations at a single moment in time. We weren't interested in what happened as something was evolving. We were interested in what was happening at that moment. Well, that's the idea behind questions like, what is the revenue when 100 items are sold? That's a relatively easy problem to solve because, oh crap. In calculus, on the other hand, what we're going to talk about is something called dynamic situations. Situations that are fluid. They're changing as time passes. At what rate is the demand for a product changing? Between May 31st and August 31st, how much did the price of a cruise increase or decrease? How fast is a car moving after 2 hours? They start out going to Nashville and they drive for 2 hours. How fast is the car actually moving after 2 hours? What rate of speed are they going at? What's the growth of a population? When does the growth of a population begin to slow down? Population doesn't grow forever. Sometimes they decrease. When does that growth rate slow down? Not when does the population decrease, but when does its growth start to decrease? When is it growing not as fast as it was before? And the techniques of calculus is going to allow us to answer these kinds of questions, which deal with what we call rates of change. And as I mentioned, a rate of change is in fact a slope. So, slope is more than just rise over run. It is how much is the output changing per unit of change in the input, or how much is the range value changing, how fast is the range value changing, depending on what you do to the domain value. So the key idea underlying calculus is the concept of a limit, which is a little fuzzy and kind of hard to get your head around. So we're going to begin by talking about limits a little bit. But, you know, don't beat yourself up if you kind of go slow in understanding this. This is not something that you've seen before. This is a brand new idea, and it takes time. So don't get impatient with yourself if you don't get it right away. Do let me know if the math is difficult, because the math itself shouldn't be difficult. The idea is one that's a little hard to get your head wrapped around, but the math itself should be easy. So if you're having trouble with the math, you need to let me know. So here's our first example. Our first example says, what happens to f of x equals x squared when x is a number very close to, but not equal to, 2? Now that's the whole idea that's going to be different for you with a limit. You're not going to just plug in a number and say, okay, this is what the limit is, because it doesn't always work. And what we're trying to find is a limit. So we first have to think about the idea of, well, just what is a limit? Well, if f of x is x squared, and we were trying to find out what f of 2 was, that would be easy. We would just say 2 squared equals 4. And that means that f of 2 is equal to 4. But that's not what a limit is asking us. It's asking us what's happening to the function as the number that we're approaching, as we approach that number. How is the output, the 4 in this case, how is that changing as we use numbers that are close to 2 but not 2? And in order to do that, we're going to use a calculator. So we're going to take a calculator and we're going to fill in this table. And the way that we're going to fill in the table is we're basically, you know, you can use the calculator any way you want to. If you know how to set up the table and build a table of values with these input values, you're perfectly welcome to do that. I do teach that in Math 1630, but not everybody necessarily remembers. We will go over that again. But, you know, basically right now all you really need to do is just get your home screen on your calculator where you do some arithmetic. And we're going to talk first about the idea of approaching 2 from the left. Now, what does it mean to approach 2 from the left? Well, if you have a number line and we place 2 on it, numbers to the left of 2 are numbers like 1 and 0, and on down here somewhere -1. But we want to get close to 2. Well, one number that's close to 2 is 1 9/10. That's pretty close to 2. It's not 2, but it's close to 2. So we could square 1.9. And using a calculator and squaring 1.9, we see that 1.9 squared is 3.61. So in the table we'll enter 3.61. And then we're going to do the same thing. We're going to try to get a little bit closer to 2 by going to 1.99, 1 99 100ths. So if you get that close to 2, you're only 1 100th away from 2. And when you square 1.99, what you get is 3.9601. So again, moving a little closer still, what if we went to 1.999, 1 999 thousandths? Well, if you square 1 99 thousandths, what you'll actually get is 3.99601. And if you move even closer to 1.9999, 1 and 9,999 ten-thousandths, 1 10,000th away from 2, which, you know, 1 10,000th away is pretty close. It'd be hard to get much closer than that. And when we take $1.9999 and square it, what we're actually going to get is a really large number as far as the number of digits, but it's actually a number that's getting closer and closer to the number 4, because it's 3.9960001. And you have to admit that's getting pretty close to 4. So what we see happening here is that as x approaches 2 from the left, what happens is that f of x approaches 4. Now similarly, we can also approach 2 from the right. This is to the right of 2, and numbers to the right of 2 are numbers like 3 and 4. So if we approach from the right, we want to get pretty close to 2, so we don't want to do like 2.5. We might want to try like 2.9, but that's closer to 3. So what we're trying to do is we're trying to get close to 2. And if we're going to get close to 2, we want to start at a number like, oh, I don't know, maybe 2.1. That's only 1/10 away from 2, just like 1.9 was only 1/10 away from 2. So if you let x be 2.1, which is pretty close to 2, it's just a little bit more, and you square that number, then you see that 2.1 squared is 4.41, which is sort of close to 4, just like 3.61 was sort of close to 4, but not that close. So we think, well, let's move a little closer to 2. So we already know that we're at 4.41 if we're at 2.1, but what if we take 2.01? Well, 2.01 is only 1/100th more than 2. And when we square that number, we get a number that's 4.0401, which is indeed a lot closer to 4. Now, again, moving a little closer, we can try 2 1/1000th, which is, again, only 1/1000th more than 2. Just like here, we were only 1/1000th less than 2. And when you square 2 and 1/1000th, you get 4.00401, which is 1 and, let's see, 4,001 tens, hundreds, thousands, 10,000s, 100,000 millionths. So it's 4,001 millionths more than 4. That's pretty close to 4. But we want to scoop just a tiny bit closer still. So our star performer here, we're going to try 2.0001. Oh, wait, too many zeros. Sorry. Let's get rid of that 0. And we're going to square that. Although that number would have been fine, we would have just gotten an awful lot closer to 4. And here we see that the number that we get in this square right here is going to be 4.000400001. And that's tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. So it's 4,000, let's see, 40,001 100 millionths. So that's pretty close to just 4. So here's what happens. As x approaches 2 from the right, getting closer and closer, f of x approaches 4. which seems kind of, why did we go to all this trouble when we knew that 2 squared was 4? Well, there's going to be equations we're going to deal with that are not going to be quite as straightforward as f of x equals x squared. So that's why we're learning how to build this table. So here's what we've learned so far. If you're trying to find a limit, one of the ways you can do it is build a table of values. And that table of values, which I've printed here much more neatly for you, shows us that as x approaches 2 from the left, which we write x with an arrow for approaches 2, and when we're approaching from the left, that's always from the negative side, f of x approaches 4. And what we also see is that if x approaches 2 from the right, which we write as x approaches 2 from the positive side, then we see that f of x again approaches 4. It's not that we're totally uninterested in the fact that f of 2 is 4, but we're interested in what happens as x gets closer and closer to 2. Now, the calculator is easy to use to make a table that shows the information a lot easier than calculating it all by hand. And we can use the graphing calculator to explore the same idea in the next problem. But for now, to pursue this problem a little bit further, just a reminder, the phrase x approaches 2 from the left is written x approaches 2, and from the left is always negative, and x approaches 2 from the right is always written positive. And we see here that as x approaches 2 from the left, we get 4. And similarly, as x approaches 2 from the right, looking at the graph, we get 4, which means then that our limit is 4. The reason I'm making a big deal about that is because those are what we call one-sided limits. The limit from the left, which is as x approaches 2 from the negative direction, is written this way. The word LIM stands for limit, and underneath it we write x approaches 2 from the left, and then we write the name of the function. Or you can write the limit as x approaches 2 from the left of x squared, since that is in fact the function. So either one of those is acceptable. And in both cases, we would say that the limit as you approach from the left is equal to 4. And this is demonstrated on your graph by the red arrow approaching from the left. Similarly, when we talk about approaching from the right, as x approaches 2 from the positive direction, and we want to write the limit we write the limit as x approaches 2 from the right, right being positive, of f of x, or the limit as x approaches 2 from the right of, in this case, x squared. That's the name of our function, or the rule for our function. And in both cases, again, you see with the blue arrow approaching the x value of 2 that the limit, or the f of x value, approaches 4. Now, the reason we made a big deal about the one-sided limit is because now we're going to talk about two-sided limits. And this is very important. A two-sided limit, such as, and this is the way you write a two-sided limit, limit as x approaches 2 with no signs either side. This implies that you're coming from both directions, of f of x, exists only if both one-sided limits exist, which we've already established they do both exist, and they are the same. In other words, they're equal. So this is what this is saying is true. If the limit as x approaches 2 of the function from the left is equal to the limit as x approaches 2 from the right of the function, then that tells us that because they're equal, and this is the most important part, they have to be equal, they have to be the same value. The limit as x approaches 2, regardless of direction, of f of x, and in this case it equals 4 because our function is x squared. So we have at this point arrived at the definition of the limit of a function. F is a function, and A and L are just real numbers. They're just numbers. You can pick any number you want. The point is that A is what we're going to let x approach. As x takes values closer and closer, but not equal to A on both sides of A, the corresponding values of f of x get closer and closer, and perhaps equal to, it may or may not be, the same number, L, which is the limit, and the value of the function can be made as close to L as desired by taking values of x close enough to A. Then L is called the limit of the function. Now, the idea of close enough to A is the idea of marching up closer and closer and closer and closer and closer and closer and closer to whatever A is from both sides. So hopefully you're not too confused by the whole idea of a limit. Hopefully this will become clearer. A little more explanation. The definition of a limit describes what happens to the function. That's what a limit does. It talks about what happens to the function, which is f of x, when x is close to, but not the same as, some number, any number, A. And that limit is not affected by how or even whether f of a is defined. For example, if f of x is equal to 1 over x, and we want to find the limit as x approaches 0 of f of x, well, we can approach 0 from the left and no problem. We can approach 0 from the right, no problem. But if x equals 0, we have 1 over 0, which is undefined, and that's a problem. But the limit can still exist, even if that happens. Also, the definition implies that the function values can approach to different numbers. In other words, if you had a function where the limit as x approached 4 from the negative was equal to 5, and the limit as x approached 4 from the positive was equal to 9, then the limit as x approaches 4, the way we say it is DNE, for does not exist. And we'll look at an example of that in a few minutes. So we'll continue here with an example. We're going to need some algebra skills here. We're going to need to be able to factor out a greatest common factor. But the first method that we're going to take doesn't take any algebra skill. It takes calculator skills. So here's what we're going to do. The first thing we're going to do in this method is we're going to build a table. Now, it's exceedingly important that you notice some things about this table, this whole process. First of all, when you go to your y equals menu, which means you just press your y equals button here, it's very important that you realize that you need to put parentheses around your numerator and your denominator, number one. And that's because the function x to the third minus 2x squared over x minus 2 means that this whole expression is going to be divided by this whole expression. If you don't put the parentheses in, as I showed you, what your calculator is actually going to see is x cubed minus 2x squared divided by x, subtract 2. And since x cancels x squared and makes it just x, what your calculator thinks that is x cubed minus 2x minus 2, which is not the same. You'll be looking at a totally incorrect function. So there's one caution. Caution number 2, and this comes from back when we were in 1630, you want to be sure none of those plots are on. If the plot is on, if there's a black box over any of those, put your cursor on top of that plot, press the enter button, and then your down arrow button. You want rid of that plot. Now, when we use the table method, and we did this in 1630, so this is a reminder, what you want to do is you want to hit your second and window key, which is what takes you to table setup. And it's important on there that on the third line down, that your independents say ask. The other one can say auto. That's really terrible. I need to rewrite that. I feel your pain when you have trouble writing on these things. So make sure that's set up that way, and then what you're going to do is you're going to go to your table with this function. This is the function. And you're going to go to that table, and the way you're going to get to your table is just press second and graph. That will take you to your table. And you're going to enter in the value 1.9, 1.99, 1.999, and 1.999 being 4. And notice that it looks like I entered 2 for that last entry. But I didn't. If you look down here, it says what I actually entered was 1.99999. And the reason I'm pointing this out is because if you use your right arrow key and get over here on the 4, you'll notice it says 4 in the table. But the fact of the matter is that Y value is actually 3.99996 in this case. And the reason for that happening is because these tables are limited to 5 digits. And here we have 1, 2, 3, 4, 5, 6 digits. Same here. 1, 2, 3, 4, 5, 6. There's actually 6 digits there. So be sure that you understand that just because you see something in the table doesn't mean that's actually what it is. Put your cursor on that number and make sure that you look at what it actually is. Because here we're also going to enter the numbers just like we did the table for the first problem. We're going to start out 2.1, 2.01, 2.001, 2.0001, and then add one more 0, you get 2.00001, which again is 6 digits. It can only show you 5 digits, and when it rounds to 5 digits, it looks and says, oh, well, that's 2, and that's what it puts in the table. The same thing when you move over here to the 4, is it's going to show you that 4 is not actually 4. It's going to be 3.99996 again. It's going to be really, really close, but not quite. Okay? Actually, it's going to be, see, looking at the previous value, it's going to be 4.00000004. Now, the last thing I actually did was I really did enter the number 2. This is very important that I want you to see why I did this. I actually entered the number 2 into that table. And the fact that I put the ask lets me plug in the values, so that's how I'm able to plug these in. Notice here when I entered in the number 2, I got an error. And the reason I got an error is if I let x be 2, then 2 minus 2 is equal to 0. My function is not defined at x equals 2. I want you to remember that. But I can still take the limit, because the limit as x approaches 2 from the left is 4. And the limit as x approaches 2 from the right is 4. Okay? Now, we can also investigate this particular limit algebraically. And the way we want to do this algebraically is we're going to factor the numerator and see if we can simplify this function. So when we factor the numerator, we see that it has a common factor of x squared. And x squared times x gives us the x cubed. And x squared times minus 2 gives us the negative 2x squared. Now, if your factoring is rusty, you'll need to do that in the skills review. So we factored that, and then we have in the denominator x minus 2. And what you notice here is that, in fact, x minus 2 and x minus 2 are common factors. Therefore, g of x is equal to this, which is equal to x squared, provided that x is not 2. Because if x is 2, then g of x is undefined. So even though algebraically that's the same, that's an equivalent function, there's a domain restriction here that isn't in this one unless we spell it out. And knowing this tells us why, when we built this table of values, that's the exact same table of values that we got when we looked at the function f of x was equal to x squared. That was the exact same table we got. You can check in your notes to verify that. Now, the third method is using a graphing calculator to graph. And basically, you just need to go through the steps that I'm showing you here. You already have your function in y equals. And when you graph it, it'll actually show that. What I want you to do to begin with, though, to give you a window where you can actually see what's going on, is I want you, after you enter your function, I want you to go to the zoom key. And I want you to choose number 4, zoom decimal. And then when you do that, I want you to go to your window key and this actually originally said 4.7, but it was negative. I want you to change that to a 0 because I only want to look from 0 to 4.7, and x equals 2 is right there. And then I want you to leave the scale at 1. I want you to change your y min value, which was originally negative 3.1. I want you to change it to 0 because we're beginning at 0 again. We're beginning at the origin. And since the value at x equals 3 is at x equals 3, which is about here, is at about 9, I'm going to have you scale your y-axis by 3. So you're going to just arrow out to the end of 3.1 and put times 3. And when you hit your enter key, it's actually going to say 9.1. I'm sorry, 9.3. Then I want you to go to your mode key. Your mode key is right next to your second key. It's on the second column of keys at the very top. And I want you to change one thing. I want you to arrow down to where it says connected. Connected will be blacked in. I want you to move your arrow over to the right, and I want you to select dot. And then I want you to hit graph. And you'll see this. And hopefully when you see that, you'll see something really interesting. Notice that that graph is not completely connected. And in fact, if you will hit your second and your trace button, that will take you to this menu, which is Calculate. And I want you to select Value, which will take you to this screen. And I want you to enter in x, where it says x equals, I want you to enter in a 2 and press enter. And notice that it doesn't give you an answer for y. And that's because if x equals 2, y1, that function that's in there, is undefined. In other words, f of x does not exist at x equals 2. Does not exist and undefined are sort of the similar and same thing. So in summary about the limits, notice that a limit can be found 3 ways. You can find it algebraically by factoring and making a simpler function. You can find it by using a graph, either drawn by hand, which that's okay, or with a graphing calculator, which is actually much simpler. Or using a table, and again, you can either write it out by hand or you can make it with the help of a graphing calculator. At this point, I'm going to stop the equation, or excuse me, stop the recording, and I'm going to complete this in parts so that none of the parts are too long.